It is a pleasure for us from Aries to have Professor Asaf Peer from Ilan University to give this online plus 2 participants here, online colloquium. Asaf did his PhD in 2004 from Weizmann Institute under Alex Waxman, and then he worked in the University of Amsterdam. He received the Riccardo Giacconi Fellowship at the STSI. In 2010, he became a research associate in Harvard Center of Astrophysics. And in 2012, he got a faculty position in University College Cork in Ireland. And in 2018, he was invited by Ilan University to set up an astrophysics group there. So since then, Asaf is in Ilan University. And Asaf actually was a colleague of one of our faculty members, Kuntal. And I met him last year in Barcelona while he was giving a very energetic talk. So I'm looking forward to this talk. Asaf, you have 1 hour. And one request for the online participants, please be mute. If you want to ask a question, raise your hand. Thank you.
Okay, so I hope everything will go well as terms of the technicalities. I'll do my best. If you cannot hear me or there is some technical problems, please let me know, of course, so that I will stop. So first, thank you very much. It's an honor and a pleasure to give this seminar. Unfortunately, just online, but hopefully we could meet face to face when times get better. So thank you very much, Indranil, for the invitation. This is I call this talk a new thoughts on the prompt emission of gamma ray bursts, and I will discuss several works. I mean, I will give general introduction first, of course, for all of you who are not working in this field, and then I will discuss more recent works that we've been doing. And as you can see, there is several collaborators that I will be talking about the works that they did. These are listed here in alphabetical order. Just briefly, Damian Biguet, Nerelli Biguet, David Eichler, Christopher Landman, Kota Murasse, Philip Samuelson, Felix Wright, and Mukesh Vyas, whom I believe some of you know quite well. So this is the outline of the talk. I will start by giving a brief description of what are gamma ray bursts, what are we seeing, why this is interesting. And then I'll go to discuss some recent results that we got on analyzing the prompt emission data. Then I will discuss the theory, efforts that we've been carrying out in the last decade or so on understanding the observed signal, and especially the possible role of the photosphere as, and ways of broadening the Planck spectrum to match what we're seeing. I will discuss photospheric emission and polarization from the relativistic jets. Then I will shift a little bit to different works about some implications that we've been doing recently about gamma ray bursts and cosmic rays. I'll give you the bottom line. I think they're not really related, not to the high energy ones. And then I will discuss a recent model that we're developing, which is a different model about understanding prompt emission in terms of backscattering dominated prompt emission model led by Mukesh Vyas. Let's start from the start. So gamma ray bursts, as you all know, these are just bursts of gamma rays that appear at randomly in the sky, rate of a few per day. When they appear, they outshine the entire gamma ray universe. This is an old movie that I just uploaded. The light curve looks pretty much like a zoo. Some of them are really short, less than a second. Some of them are longer, lasting for a few seconds. Some of them have a single pulse. Some of them have two pulses. Some of them have multiple. Quite nasty. Generally, they last for a few seconds, and the variability is seen for tens of milliseconds, pretty much limited by the detectors that we have. Now, if we look at the spectrum is mainly at the gamma rays, obviously, right? So peak at the sub-MeV range, and the observed flux that is seen by the detectors in this range is about between 10⁻⁷, 10⁻⁴ ergs per centimeter square per second. The spectrum is by large non-thermal, and extend in some cases to gamma rays, right? Just I gave a short slide, right? So we're talking about somewhere around here, but extends to GeV. Sorry, of course, it's the gamma rays. The typical peak energy is of the order of MeV, and there is this broken power law typical shape known as the band function, which is right here. So this is simply followed by David Band, the late David Band, who was the first to put it on paper like that. It's a very simple model, which is mathematical in nature, right? It's simply a broken power law, right? With a low energy spectral slope, high energy spectral slope, peak energy in between, and of course, overall normalization. So it has only 4 parameters. It provides a reasonable fit, surprisingly reasonable fit to the data of very many different bursts. Although in some bursts today, we know this is not enough because there is also the GeV emission. This is quite old slide I have. And most importantly, it is mathematical in nature, right? It doesn't tell us anything about the physics of gamma ray bursts. It just gives us some empirical way of describing it. Now, as of the 90s, we know that there are 2 different populations of gamma ray bursts. One is the shorter one, and one is the longer one. And the shorter one tend to be harder. So when we say hard, we just look at the flux and the high energy band, 100 to 300 keV. That's the typical one, divided by the flux at lower energy ranges, 50 to 100 keV. And you're clearly seeing this bimodality distribution, which occurs. And that naturally raised the idea that there are 2 separate progenitors, 2 separate ways of producing gamma ray bursts. Roughly about 1/4 of bursts is in the category of the short ones, and 3/4 are in the category of the long ones. And you know, this general picture hasn't changed over the years. Another thing which became evident in the 1990s is that the distribution in the sky is isotropic, which means that the origin is not galactic, because otherwise they would be coming from, you know, mostly from the galaxy, but rather extragalactic, meaning cosmological distances. So we know since the 90s that they come from, you know, distant galaxies. Now, briefly, this information, which became evidenced by the mid-1990s, is enough to give us the realization that we're talking about some very interesting phenomena. And here is one slide that summarizes all of that, right? So if we know that the observed flux is of the order of 10 to the -7 to 10 to the -4 ergs per centimeter square per second in the detector, in the satellite, and we know that they come from cosmological distances, then, you know, if they're isotropic, so spherical explosions, then we know that the total luminosity is the flux times 4 pi the distance squared, which is of the order of 10 to the 50 to 10 to the 53 ergs per second of photons that are being released in a few seconds. Now that sounds a lot, and that is really a lot, because if you compare that to the solar rest mass, m sun c squared, is about 10 to the 54 ergs, which means that in these explosions, there is a release of a few percent of the solar rest mass in gamma ray photons per, you know, in a few seconds. Now, furthermore, we know that the variability is very rapid. We talk about 10 milliseconds variability. And light crossing time argument means that the source size needs to be smaller than this variability times the speed of light, so a few times 10 to the 8 centimeters. So we're talking about a few tens maybe of Schwarzschild radii of a solar mass black hole, which means that the object that produces them, whatever it is, must be a very compact object. So we're speaking about a very small compact object, right? The radius of the sun is about, you know, 100 times or 200 times larger than that value. We're talking about something which is much smaller that releases a huge amount of energy in a very short time, only in gamma rays. Now, theoretically, that implies even something which is even much more interesting, and that is that the number density of photons at the MeV range, right? We can estimate this at least to an order of magnitude by knowing the luminosity and the size. So just the luminosity divided by 4 pi r squared times c times the energy of photon, the MeV, which is what we're seeing. And we know that these photons, the reason why I look at MeV photons is because we know that these photons can produce pairs, and we can look at the optical depths for production of pairs, right? 2 photons interact and produce a pair of electron and positron. And we end up, when we put this value, the numbers here, right, the cross section, we know what it is, the size, we know what it is, and the density we can estimate from the luminosity and the energy and the size. We get something of the order of 10 to the 16, right? So even if I'm wrong by an order of magnitude or even 3 orders of magnitude, it doesn't matter at all, because optical depths larger than unity implies that we should not be able to see those. So, you know, we should not be seeing anything which is larger than the threshold for pair production, but of course we are seeing it. So there must be something really interesting going on here. So if we summarize all that, we know that there is a large variability, compact source, high optical depths to pair production, and we're seeing a spectrum that is non-thermal. The conclusion is that we must have some creation of a fireball produced by pairs and photons. And this is a way of transferring the energy. So we have some source of energy, energy release, which we know today is associated with the production of a black hole. And then at the first stage, it is converted to kinetic energy in the form of a relativistic jet, which at the second stage only is being dissipated, partially producing the radiation. Now, this is the way to overcome this opacity problem, because while the photons are produced, the outflow is already moving at very high Lorentz factor, and so the observed energy is Doppler boosted by a factor gamma relative to the emitted energy, or the emitted energy is a factor gamma less than the observed energy, so we are avoiding the production of pairs. And this dissipation process, whatever it is, produces the non-thermal spectrum that we're actually seeing. So this basic picture led to the emergence of this fireball model, which is emerged roughly by the mid to second half of the 1990s, and mainly by works of people by Paczynski, the late Paczynski, recent Mazaros. So we have a source of energy, right? Here it's a collapse of a massive star producing jets. Namely, this is the kinetic energy, which we cannot see. And then there is some source of dissipation process. Initially, it was thought these are internal shocks. We know today these are not really efficient. Possibly now people think of magnetic dissipation, which produce the gamma rays. Now, this whole picture, if this is correct, gives a clear prediction, which is the afterglow, which is that when this jetted material emits the gamma rays, but then it continues to run into the interstellar medium, gradually slowing down, heating it, and producing afterglow emission from the X-ray, which gradually goes down optical and radio. And indeed, this was detected as of 1997 and gave confirmation to this general picture. Now, I should say that, you know, this picture is with us for about 20, 25 years or so. And despite the fact that we don't really know and we don't really understand many of the details, the general skeleton of this picture is quite accepted by most of the community. Now, let's look at, I'm focusing on, of course, the afterglow. I should just say one word, right? The afterglow lasts for much longer than the prompt emission. It's much smoother. This is a stage where the flow becomes self-similar, so it's much easier to analyze the data. So a lot of work is being focused on the afterglow. The prompt, as I said, is much more difficult to analyze because it's variable, it's very short, it's unpredicted, we don't know where to look for it. So it became a challenge much longer than the afterglow. Now let's look at the recent prompt emission data and try to see what we can say. So I told you that the prompt emission of gamma ray bursts is, you know, traditionally, since the mid-1990s and until today, is by large being fitted with this so-called band spectral fit. Again, this is named after David Band. It's a simple mathematical model, 4 parameters, provides acceptable fits to the data and mathematical in nature. Now, because it's mathematical in nature, it means that we need to provide some physical interpretation, and people have started to look at physical interpretation. And the initial suspect, as usual, was synchrotron, which is possibly associated with Compton at higher energies. Now, synchrotron has, you know, it's very natural because we're seeing synchrotron emission everywhere in astrophysics. Each one of you is an astrophysicist, I'm sure, that encounters synchrotron at a certain point in time. The theory is very well understood, right? Since the 1960s by Ginzburg and Sirovatsky, you can find it in standard textbooks, Rybak and Lightman, for example. And as people noted, of course, we don't really know the values of the parameters, but when you put values which look reasonable for the magnetic field, for the Lorentz factor of the electrons, of the outflow of a few hundred, of the thermal motion of the particles of about 1,000 or so, we end up with values of the peak frequency, which seems to match pretty much with what we are seeing, the sub MeV one. Here it's 500 keV. And also the peak flux, again, that depends on how many particles we have there, but it seems to match quite nicely. So the initial suggestions were that it's most likely what we're seeing is due to synchrotrons simply shifted to these high frequencies because the values of the parameters are so much different than what are used to from other objects in astrophysics. Now, however, already by the late 1919, by the way, have lost connection? Can you hear me? Guys?
Yes.
Yes, I can hear you.
I got some note that my internet connection is not stable, so I stopped for it. Are you still with me? Haven't lost me?
Yeah, I can hear you.
Good. Okay, very good. So I'll continue. So from the late 1990s, when enough data became accumulated, people started to look at the spectral slope, not only at the location of the peak, but also at the spectral slope. And what they realized is that the spectral slope is much harder than what the theory predicts, because we understand the theory so well, the synchrotron theory, then we know what are the limitations of the theory, and we can match that to the spectral slope, and we see that it doesn't match. And that led Rob Preece to coin the term synchrotron line of death. Basically everything with alpha, which is greater than minus 1.5, well, the average here of alpha is minus 1, what you're seeing in this DF nu already knew, so just not to get confused, is inconsistent with synchrotron. The reason is that the photons should cool down very rapidly in these strong magnetic fields that are there, and we know what is the spectral slope that we should see from these cooling down photons. So a work by Magnus Axelsson from 2015 showed that about nearly 80% of long GRBs and 85% of short GRBs are inconsistent with synchrotron. So that means that there must be something in addition. This is another way of showing that, this is what the synchrotron theory would tell you. These are real data taken from a certain gamma ray burst. And the synchrotron theory will tell you, okay, this is the slope I would expect to see. And the slope that I'm actually seeing is much steeper than that. And this is something which repeats itself all over in these bursts. Now I should say, to be fully honest, that in recent years, there has been some revive of the idea of synchrotron when people started to say, okay, maybe we can make it work. And I'm referring you to a paper by Bruguez et al. From 2020 saying, actually, possibly we can make it work. But when we look at the details, it requires the unacceptable, to my view, ratio of total energy to total number density, which should be more than 10 to the 7, while we expect to be of the order of 1. Or alternatively, it might work if we only have fewer of the electrons being accelerated while most of them are not, so that to avoid this fast cooling. So they propose mini jets. I mean, so there are all sorts of dynamical suggestions that might make the synchrotron work. After all, which maybe they are, but they require some sort of I would say manipulations, which I'm not sure of. What I want to focus now, okay. The alternative, of course, is that this is a motivation of studying the alternative emission, which is the photospheric emission, which I will say a few words about in a few minutes. Now, I think that the Rosetta Stone came in 2009, 11 years ago. This is a gamma ray burst, quite famous, 0909 or 2b. The phone numbers are just the dates in which they were detected. And what's unique in these bursts, there are two really unique things. One, it was a very bright one. It was one of the brightest seen until today. I think it's the second or third brightest being detected. Now, it did show this spectrum, which was very, very steep, very, very narrow, absolutely could not be explored by synchrotron. But you know, people that like the Singleton model did not get too excited. They say, okay, we know that GRBs are a zoo, so some of them are like that and others are like that. But to me, the second interesting feature of that was because it was so bright, people could do a time-resolved spectral analysis. Now, often when people do the spectral analysis, of course, there's not enough data, so they just have to gather enough data to do the spectral analysis, which means that you have to integrate over time, right? There's always this trade-off. You need to have enough data so that you can say something about the spectrum. Since this burst was so bright, people could have done time-resolved analysis. And what they saw is that within a single pulse, the spectrum changed. It actually opened up. You saw a spectrum which was initially narrow, very narrow, consistent with having a Planck spectrum, but opened up in time. And that implied that if we wanted to say something useful about burst, then we must use a time-resolved spectroscopy, because only then we can pinpoint the true nature of the mechanism. Now, understanding that, I'm going to describe a work that we just carried out. That's my hero one. So first, you know, the pure Planck, you know, we teach that in undergraduate level, right? You know what is there's the Rayleigh-Jeans tail and there is a wind peak, and we know how the spectrum should look like. But in reality, there is some sort of an aberration, and we're expecting the low energy spectral index, I'll speak about this aberration in a few minutes, to slightly modify over the Rayleigh-Jeans part. So Andrei Belobordov have shown 10 years ago that the light aberration would cause low energy spectral index to be roughly 0.4, not the 1 that you get. But this depends on the bandwidth that you're looking at, right? If you're going closer to the peak, then of course the spectrum that you're expecting to see is going to change. So we have to take this limited bandwidth into account, because when we're looking at the data, the bandwidth is always limited. And two works actually, which were carried by Zeynep Akuner, show that when she carried the time results analysis of pulses in long gamma ray burst, she found that more than 25% are consistent with having a pure black body. That is, that the other ones, so they are so narrow that they lie above these lines. So they must be very, very narrow. Now, a work which was led by Husna Dereli earlier this year, when it was published in UpJ, showed that when we look at the short GRBs, then 25 out of 70 of the pulses of short GRBs in the GBM catalog, when you do a time-resolved spectral analysis and you look at the narrowest time step, then you find that more than 1/3 are consistent with having a pure thermal origin. So when we put those on the E peak and alpha, then 1/3 lie above this line, which means that they are entirely consistent with having a pure thermal origin without the need even to have any interference, any broadening of that spectrum. When we continue to analyze that, we find some really interesting results here. For example, we find that the peak has what looks like some sort of a bimodal distribution. I'm now only looking at the peak of those bursts which are above this line. So they are entirely consistent with pure thermal origin to 1 sigma level. That doesn't mean that the other ones are not consistent with it. It just means that these ones, I just don't need to add anything to them. And what we found, these are the T90 distribution, the hardest ratio. These are the long GRBs here, and the red and black are the short GRBs. And you're seeing that the black ones are the ones, the red and blacks are all of them, and the black ones are the ones that are above these lines, so they are fully consistent with thermal. And you see what looks like a bimodal distribution. So the ones that have a lower E peak seems to be a continuation, forming a continuation of the long GRBs, and the ones that are shorter tends to be harder. They seem to form a separate population, which raises the idea, which I don't know, right? But raises the idea that possibly what we call short GRBs may actually be containing two separate populations. And I'm talking now only about the short GRBs, not what happens within the long and the short. It's an interesting idea, which we're definitely thinking of exploring further. All right. Can you still hear me? Anybody?
Yes.
Yes, good.
Okay. So now let's go to the next part, which is a little bit about the theory. What causes the observed signal? So I put this slide again just to mention that, you know, within this general picture of the fireball, and when I say fireball, I'm not limiting myself to the classical one. So for me, fireball is also models which are highly magnetized model. It's a general picture where you have a gravitational energy which is converted to kinetic energy, could be directly mediated by neutrinos, could be mediated by magnetic fields. And then at the second point, this is converted to photons, to the radiation field that we're seeing. The problem with the variability is that it requires several emission zones, which means there is no real predictivity here. But the important thing is that in all of various types of these models and all various suggestions, all of them have something in common, which is the existence of a photosphere, right? Early, if you go very deep in the flow, the matter is dense, so optical depth is large, and so photons cannot escape from there. And when you go outside, you know, to a certain radius above it, the density becomes smaller, the optical depth becomes small enough, and photons can escape. So there is some radius, which is obviously the photospheric radius, from, you know, which is the earliest, the shortest radius from which photons can escape. Exactly where it is, that depends on the parameters of the model and exactly what nature of model you assume, if you have a kinetic model or you have a magnetic model. But, you know, there is something in there. So this is something which is, you know, similar to all of these models. It's something which is inherent to all of them. Now, if what we were to see was a pure Planck, then, you know, I plotted here again this plot. This is the data that we're seeing. This is what the Sinnerton model would tell us roughly, right? So it's too flat. But Planck, on the other hand, right, it's too steep. Well, we're not seeing that, except from this special case, this 09 and 2B. Most bursts we're seeing is not as steep. Now, the basic idea that we came up with a while ago was that, you know, it's much easier to take a narrow spectrum and broaden it, open it up, than taking the flat spectrum and push it down, right, and make it narrower. So we started to think of various ideas of how you can take a Planck spectrum and open it and broaden it up. Now, the important thing to realize is that there is a difference when we're saying photospheric emission. We do not necessarily mean thermal emission, right? Thermal black body is what you'd see, but here we have various sources of aberration which would cause the photospheric emission, meaning emission that comes from this photospheric radius, to be different than a pure black body, right? Now, there are various ways. I'll speak about one of them, which I call a geometrical broadening. There is a physical broadening which relates to the interaction of particles and photons below the photosphere. I simply won't have time. I'm already too crowded with slides, so I'm just going to skip that. Maybe next time, if you're interested, I can speak about that. I'll speak about geometrical broadening a little bit, because this is also related to another work we're doing right now. So what's the idea? You know, think of a sphere which explodes. So the arrows here, the black arrows, represents the electrons. They have a relativistic wind. And then you have two photons that are ejected from the same radius, right? Emitted from the same radius and propagate towards the observer, which sits somewhere over here, right? Just by looking at this small cartoon, it's obvious that the optical depth, or the path, the light path that these photons have to go, is different than the light path that that photon has to go. Simply has to cross more electrons. This is another word of saying that the photospheric radius is in fact a function of the angle to the line of sight. Now, when you do the math, you end up that it's actually a very simple function of the angle to the line of sight. It's just some constant which depends on the outflow parameters times theta over sine theta minus beta, right? Theta is just the angle and beta is the velocity of the electrons. Now here I'm just assuming a constant velocity over space. For small angles and high Lorentz factors, it just goes as theta square over 3 plus some constant 1 over gamma square. Surprisingly simple, and this is how it's plotted here. The photospheric, so the photospheric radius is in fact, it's not a radius, right? It's just a shape, right? It's a concave shape, which looks like a ball of some kind. Think of it, it makes a lot of sense when you're speaking about spherical explosion, but it's not trivial, right? Many works just assume it's a 1D, so it's just like a one point.
Asaf, one clarification. Why are you considering a relativistic wind and not a jet?
It's the same. Gamma of 300, it's a jet. I just call it a jet. Just call it a wind, just for the sake of the slide. Okay. Right? I just assume a spherical explosion which causes particles to flow relativistically at some velocity beta. Here I just put it as a gamma.
Oh,
that's it. It's the same thing.
all right.
Okay. Now, when you think of it some more, right, in the setup that I had, it's a very simple setup, right? You have electrons moving away in all directions at the same speed, which means that the photons have some finite probability of having their last scattering position everywhere in space, right? So it's not just a single line here which represents this optical depth tau equal 1, which is really a mathematical entity. What you're seeing here is the result of a Monte Carlo simulation, which I built a few years ago, which shows the last scattering locations of each individual photon on this space, right, as it propagates. And using that led to the concept of a vague photosphere. So what we speak about the photosphere, right, it's like a cloud essentially, right? There is some probability of a photon to be scattered from anywhere in that in space. And the only way we can really describe it is by probability density functions, P of R and theta, which you can actually get quite a good approximation to, right? In other words, what this really gives us, I'm not going to get into the mathematical details. It's really interesting, but it's just mathematical. It means that you are seeing a lot of emission from higher angles, which is essentially the limb darkening effect that we're seeing in the sun and other stars, of course, only applied to relativistic outflow. But in relativistic outflow, this limb darkening is essentially much more pronounced. Now, this was done in 2008, and then 2011 we continued this work. But then we thought, hey, I mean, spherical explosion is not what we have, right? What we have really is jets. Right? Jets have some profile. Right? Now, we're not sure what the profile is. Here we have to rely on numerical simulations, but we do have some numerical simulations, which are there since the 2000s. Which give us what is the profile of the Lorentz factor was a function of angle. So we can estimate that, initially the Lorentz factor is higher, but it drops down quite sharply with angle from the jet axis. When we do that, right now we have to simulate some sort of spectrum, some sort of jet profile. So we simulate the jet profile, which goes like that. So it's roughly constant up to theta jet, and then it drops down like a power law. This is the constant that we have. And of course, now we have several parameters to specify the flow. It's not just the Lorentz factor. Previously, we just have a single parameter. Now we have what is the gamma zero, right? What is the jet angle? But what is this power law? How do we quantify this decay? And also the viewing angle. Now it becomes important where is the observer sits. Now, when we do that, when we repeat this calculation for what we consider to be a more realistic scenario, and we consider that based on numerical simulations, we find out that the limb darkening effect becomes much more pronounced. We have many more photons coming out from the sides, which is kind of easy to understand because that a little bit depends on the assumption we're putting about how the photons are ejected. But here we're simply assuming that you have a lot of these side photons, and we're saying that this limb darkening effect becomes extremely pronounced. So when we do the overall spectrum, we ended up with something that looks like that. I mean, this is the global spectrum that we're expecting to see. This is a work that was led by former PhD student Christopher Landman. We basically separated to three different parts. There's the inner jet where gamma is approximately constant, and that produces the peak that we're seeing. And then there is this outer jet where the jet decays, and that produces, of course, emission that goes at lower energies. And then there is this envelope, which produces something. But again, this really depends on what is the luminosity, how is the angular dependent of the luminosity that we're assuming. The takeaway message is that, we managed to retrieve this kind of spectrum without, this is pure photospheric, right? I mean, this is, if you look at such a spectrum, we would never say this is a black body, right? This is a thermal, because it doesn't look like a black body. But, this is simply aberration of light. That's why I call it geometry, right? We started from a black body. All the photons here are thermal. They're just having different scattering angles. And so they suffer different, Doppler boosts. And if you're looking at different angles, apparently the exact angle is not very, the exact viewing angle is not very important. This is for different viewing angles. The peak pretty much matches what we're seeing, sub MeV, for plausible parameters of the luminosity and the Lorentz factor. Now, but there was another very interesting feature which was discovered by, by the code really. I didn't foresee it coming. And that is that when we make the spectral, the jet profile steeper, so larger P, we ended up with what looks like a rising high energy tail. And when we think of this rising high energy tail, where it comes from, we figure out that there is a very interesting phenomena here, which is the fact that a photon below the photosphere is being scattered multiple times in regions of different velocities. And what happens is, and you can show it, it's not a very complicated to show, you're having two effects. One is that when you have this scattering between regions of different velocities, it acts to focus the photons. Their angle is more focused, it's less spread, and also they can gain energy, which is essentially coming on the expense of the kinetic energy of the expansion. So this process is essentially, it's a very analog to a Fermi process in which electrons are being accelerated by going back and forth from a shock wave. Here we have photons that go back and forth in regions of different velocities. And on the average, you can show that they gain energy. And this gain of energy ended up in a power law spectrum with high energies, which is kind of nice. Now, another very interesting feature of that, is polarization. I mean, we know that Thomson scattering produces linearly polarized light. Now, what we have here is entirely scattering. That's what we have. We just have scattering. So, a necessary condition for us, of course, a necessary condition for us to see something, some polarization signal, is that the photon field would be anisotropic. Right now, of course, deep inside the flow, that doesn't happen. The photon field can be considered fully isotropic. This is a plot taken from Beloborodov, right? But as you go nearer and nearer the photosphere, then the photon field becomes less isotropic because the photons are pointing away from the jet. Now, from a spherical outflow, right? If you look at the emission from angle of 1/θ, you find 100% polarization. But of course, you wouldn't see it if the flow was actually spherical. But if the flow is not spherical, something like that, and if the observer is not sitting on the jet axis, then the observer will see that, right? You will see this polarization because you will see more photons coming from different angles, and you'll break the degeneracy, right? So this is a plot taken from Christopher Lunsman's PhD thesis, showing how the different photons look like from observer looking at different viewing angles, right? From zero, when everything is symmetric, as the observer sits from the outside. The outcome of all that is that for an off-optical observer, we found out that you can get up to 40% linear polarization with a quite significant flux. I mean, of course, the problem is as you go to the sides and you're losing flux. And a natural prediction of this model is that we are expecting to see a 90 degrees shift in the polarization angle, because the photons go from being mostly in the y direction to the x direction. And of course, this is accompanied by the fact that we should see a broad spectrum, which does not look at all like a Planck. At low energies, we have an extended emission from a shear layer, which results in a flat spectrum. At high energies, we have a repeated scattering between the core and shear layers, which end up with some power law of that. So we have a very nice prediction here, which we want to push further. Now I'm jumping. This is a result that we started working on it from last year, led by Vidushi Sharma and Sharma Miyani, using data from the Indian satellite Astrosat. This is a gamma ray burst 160821A, which show a very nice peak, and more interestingly, it's very energetic, and it shows very strong polarization, and there is a polarization angle change of consistent with 90 degrees, and we're seeing that twice. Now I have to be very careful here because I'm not sure that what we're seeing is exactly due to the photosphere. I think that there might be something else in here. We're still working on that. There isn't the second paper, the 2020 paper, is still in preparation because we've been spending a lot of time trying to figure out what it is. Since we haven't published it yet, I can still say that maybe it is a polarization associated with this phenomena that I showed you. Not sure. Just have to, the paper, hopefully it will be published later on this year or early 2021. We're definitely working hard on that right now. Okay, I still have some more time, right? You're still with me, right? It's not too much?
Yes,
okay,
yes.
good.
Go for it.
Let's continue on to gamma ray bursts and cosmic rays. So I'm doing a little bit of a side here. High energy cosmic rays. This is a subject by itself, right? You have conferences on that subject, right? We are seeing cosmic rays at all energies, and we're most interested in the most highest energy ones. Now, there is a general plot which was done by Hillas back in late Hillas. He just died a few years ago, by 1984, which essentially says, okay, I just put it in my words, which I think is the simplest, right? We don't know what sources are producing these high energy cosmic rays, but we do know that they need to be accelerated. And we know that during their acceleration process, they need to be confined to the sources. In other words, we want to have the Larmor radius under the assumption that there is a strong magnetic field that confines them, right? So the E over QB is it's a particle's charge, whether it's a proton, it's a 1, if it's an iron, it's a 26, need to be smaller than the source size. So that gives us a constraint for a given particle's energy E on the source size and the magnetic field. So this is what plotted here. This Hillas was the first to plot it. And R times V, so for a given energy, you'll have these diagonal lines, right, which will correspond to a given energy. So for example, for protons with Emax of smaller than 10 to the 21 electron volt, which is the highest cosmic rays that we've been seeing, this line should lie here, which means that there must be some combination of source size and magnetic field that will enable us will enable the source to accelerate these particles, right? Now, what Hillas did is started to put on various objects, not non-astronomical objects, on this plot. You know, for example, white dwarfs, we roughly know that they are small, very compact objects, very small, but have strong magnetic fields. You can put AGNs, you can put IGMs, intergalactic medium shocks, you can put neutron stars, you can put whatever objects you know that you have some good estimate of the size of the object and of the magnetic field. And you ended up, not surprising at all, that in order to accelerate particles to the highest energies, you must have the most luminous sources, which essentially ended up, maybe I should do it here, either the most luminous steady sources, which are active galactic nuclei, or the most luminous transient sources, which are gamma ray bursts. Now, this is another way of showing that. I don't know if we need to go into the detail of that. The assumption here is, magnetic field, of course, we don't know what is the magnetic field, but we can convert this to magnetic luminosity if we know what is the source size and what is the Lorentz factor. And then we have to assume that we don't see the magnetic field, but we do see the photon, so we need to assume something that the luminosity that we're seeing in the photon is the same as the luminosity we're seeing in the magnetic field. Otherwise, it's called the dark sources, and then we cannot say much. So luminous steady sources, they were suggested from the 90s or maybe late 80s, right? Active galactic nuclei. And luminous transient sources, there's a gamma ray burst. So since the middle of the 1990s, where people realized that gamma ray bursts are so powerful, they started to speak about them as valid sources of high energy cosmic rays. Now I should mention, because this will be here in the talk, that there is also a subclass of gamma ray burst, which is low luminosity gamma ray burst. They are about 3 to 5 orders of magnitude less luminous than standard gamma ray burst. They're not as, the Lorentz factor is not as high. It's not like 100 to 1,000, maybe it's a few, we're not sure. And these are also being considered. And all the details here are various suggestions, external shock, internal shock, reverse shock, etc. So these are all various details. Now we try to say, okay, but maybe we can say something about that. And the key idea that we have is something which is very simple. We're saying, look, we're not sure about the acceleration of acceleration of particles in gamma ray bursts. But we are assuming something. We're assuming that whatever accelerates the cosmic rays, which are essentially protons or maybe heavy nuclei, they also, whatever mechanism it is, it also accelerates the electrons. And the electrons radiate. And we know the radiation because now we have quite a good handle of the spectra, as I just showed you, right? So we can use the observed spectrum that we're seeing to constrain the physical conditions at the acceleration site and see if we can use that to, to constrain the ability of these objects to be sources of high energy cosmic rays. So we had several physical requirements. One is about the slow energy spectral slope, right? It cannot be too shallow because I just showed you it is not. And we looked at two different types of models, right? One is zero-ton dominated, where the cooling needs to be quite slow so that we can match this low energy spectral slope. The second is a thermal dominated, and then the requirement is that the flux of the zero-ton will not overshine the flux of the photospheric. And that gives us some upper limit. And then we can use the upper limit from observation or even from non-detection in different bands, right? If the peak is in the gamma rays, then we have also from data from the optical band existing in recent years. And then we also put just the standard physics, right? The physical conditions which enable acceleration of particles to the required energies essentially imply that the acceleration time, which we can approximate it under some uncertainty in the efficiency, it must be shorter than the cooling time. Otherwise, the particles will not be accelerated. They just cool down before they accelerated. And the cooling can be either by zero-ton emission, by adiabatic cooling, or by interaction with the photons. And when we put the numbers, right, this is a paper which was led by Philip Samuelson, who was visiting us. Essentially, we find no solution, right? So we find here in the parameter space R and B, the different lines represent the different limits from the requirement that the acceleration is. So here is the photospheric radius, so it's about 10 to the 13 for these parameters. And then we have the requirement the acceleration is shorter than the loss due to photomeson interaction, loss due to adiabatic interaction, and loss due to zerotron. And we end up that, you can find some solution, but only in this range. And then when you look at the flux, which we're seeing in the 30 keV to 3 MeV, we're pretty much in here, in this range, for the cooling break. And we find out that we cannot accelerate particles, GRBs cannot accelerate particles to more than, let's say, 10 to the 17 electron volt. The highest one is about 10 to the 21. Physically, what really happens here is that they require the electrons to, if we want to accelerate particles, it means that we have to have strong magnetic fields and the electrons will cool too fast. And then we run back again into this problem of spectral shape that doesn't match what we're seeing. So we tried different options, I said. So this was the zero-ton dominated. We tried what happened if we assuming that the peak is dominated by thermal emission. Again, the plot becomes a little bit more messy because we're looking at both the optical and we're looking at the peak at the gamma rays, and we look at the different possibilities for the magnetic field. So that's why these plots look a little bit strange. And when we combine them together, the important thing is to look at this red line because this is the observational limit that we have on the flux, and nothing matches. So there is no solution. And then there was the idea that came up saying, okay, well, what about low luminosity GRBs? Maybe these are subcategory of gamma ray bursts. These are much more nearby. We know that they're connected to supernova. They tend to be extremely long, but at least 100 times less energetic than the average gamma ray burst. The rate may be quite high because if, they're just much less luminous, so we just don't know. We just cannot see them. And we're not even sure if they are associated with regular GRBs or maybe they have some different physical origin, like a shock breakout. Now, we do have one great prototype, which is 060218, gamma ray burst that was seen 14 years ago, which is very well observed. It's right here on this plot, the ISO versus E peak. And we have great light curve. This is the XRT light curve, which lasts for 2 million seconds, right? So that's several days. And we're having great spectra, which also we have spectra at early times and at later times. And we pretty much know anything about this burst, so we can use it as a proxy. And when we do that, since we also have data in the afterglow of this one, we can do the same calculation for both during the prompt phase, but also look in the afterglow phase. Here we're doing some fitting with numerical code that we built a few years ago. And essentially the conclusion, I won't go into the details because of shortage of time. The details are the same, right? There is no solution unless the GRBs are dark, meaning that only a very small fraction of the electrons are accelerated. So you can argue we haven't really nailed it down, because you can say, okay, you can have a solution in which just the protons are accelerated, but only a small fraction of the electrons are accelerated. But you know, it kind of, at a certain point, it can become a little bit boring, right? You start saying, okay, so does that make sense? Maybe, but to me, I mean, you know, it looks a little bit less realistic to say that only the protons will be accelerated by the electrons not. But I have to be careful because we don't really understand these acceleration mechanisms in full details. The same for the afterglow, right? The radio data essentially overshoots. That's what you're seeing here. The radio data essentially will overshoot the observations by several orders of magnitude. So there's really no solution. The details are found in the paper that was just accepted yesterday. So this is really nothing. Now for the last part, I know that it's a bit dense, but I do want to keep over time. I want to do some different idea, right? Something completely different. Backscattering dominated prompt emission model. Here is the idea, right? This is a work which is led by Mukesh Vyas in collaboration with David Eichler. So we know in this, I showed you that, right? When we have this gamma ray burst jet, they drill a hole through the star, but then they push away all the material, all the debris from this collapsing star. And this material forms what is known as a cocoon, right? This is a hot material made mainly from the envelope of the star, which is being pushed away. Now, many of the models assume that these jets, simply cross this cocoon and continue on. But this is not always the case because, if you think of it, what we know about these jets is essentially put by hand, right? If you look at these numerical simulations, the initial parameters of the jet is something which is put by hand. And so we know in the literature, I know at least for 15 years, people discussing the possibility of chocked jets. What about jets that doesn't make it, right? So they do manage to break a hole through this star, but they cannot cross the cocoon simply because they're not energetic enough. But the cocoon itself at this stage is already moving relativistically outwards, right? Now, what will happen if you have an emission of photons that come from the inner region, right? Then the photons will just go through this funnel, which has already been cleared up, but then it will encounter the cocoon and be scattered backward, right? But, well, scattered backward from the cocoon's point of view. But since the cocoon is already moving relativistically, then in fact, from an observer's point of view, the photon will simply be scattered at some angle, and it could definitely be seen by an observer, right? Provided that the observer is not sitting at angle of 1 over gamma, right? But that the jet could be quite large here, right? Of about 0.1 degree. So when we look at that, then we have a new model in which what we're seeing as prompt emission, in fact, comes from photons that were mainly scattered from a relativistically expanding cocoon, slightly sideways, right? They were initially emitted from deep in the flow, and then they were scattered once or twice or several times within this cocoon, and eventually they reach the observer. Now, of course, photons that were that happen to have initial different larger angle would suffer a larger Doppler boost, shorter Doppler shift, smaller Doppler shift, sorry. So they will be observed A at later times, right? Simply because of geometry, and B at lower energies. So this is what we're seeing. Looking altogether from an observer point of view, the observer will see a spectrum which will have a spectral slope of the epsilon of roughly epsilon to the power unity, which is not too bad, and a light curve, which we anticipate could change from t to minus 1 to t to minus 2. Again, now we get into the details of where exactly is the observer located, whether it's the center, whether it's somewhere in the side. Obviously, the observer will be sitting somewhere in the side. And when we look at the spectra, okay, so this is for a cold core, right? This is a non-realistic scenario, which is serve us to understand what we're seeing. When we're looking at the realistic scenario, the quark is obviously hot because it's been heated, right? So we can take a rough estimate of about 10 to the 8 degrees Kelvin, and obviously some of the photons will be scattered multiple times before they leave the quark. So this is all being simulated by the simulation that Mukesh is developing here, right? And what we have here is that when we look at the spectrum, then we're seeing several new features, right? So we're seeing some energy gain, which is mainly associated with photons. This is just a truncation of that for photons which were scattered. L is the number of scattering that we had, that the photon undergo. So photons that undergo multiple scattering gains a little bit of more energy from the core, causing broadening of the high energy spectral slope. And there is obviously a temporal evolution, and you can see that the entire light curve changes with time. And we do manage to get, for the parameters, values which are quite similar to, or match quite well with what is being observed. And a very interesting feature of that is what's known as the Amati relation. This is the E-peak and E-iso correlation, right? Amati is, noted 14 years ago, what seems to be, again, observational correlation between the total isotropic energy and the peak energy. Now, apparently here, we are managing to get a very similar result, and this is the Amati relation. The CP goes E-iso to the power 0.45, simply by considering observers that sit at different viewing angles, right? Because obviously, the observer sits at, different observers sit at different locations, or different gamma ray bursts are pointing in different directions from us. So different observers, right, seeing different peak energies, right, and also seeing different total energies. So the results we got seems to be quite in line. I wouldn't be as, I wouldn't jump and say, look, we solved this problem. I'm just saying, look, this model has some very interesting feature, which possibly may explain that. This is a paper that is currently being written. I hope it will be, we could put it within the coming weeks outside, again, led by Mukesh Vyas. So you're all welcome to watch the archive, and it will be, hopefully in the coming weeks, this will be out. So I think I'm pretty much on time. So let me summarize the takeaway message. I know it's been a bit dense because I tried to cover several of our recent works and also to give some ideas to people who are not in the gamma ray burst community. So what is the takeaway message that I got from here? So first is that gamma ray bursts are the most extreme objects we know in the universe today. It's been like that since I was a PhD student, and it still is like that. The spectra, especially the prompt emission spectra, right? It's extremely tricky to understand, but it may be explained by the broadening for photospheric emission. I did say a few words about the geometrical broadening as a new tool of studying jet geometry and polarization, which has now become quite hot topic, especially with this ultra satellite. I showed you a recent work we did, which shows that gamma ray bursts are likely not the sources of high energy cosmic rays, ultra high energy cosmic rays. And then finally, I discussed the backscattering dominated model, which opens new possibilities, such as a natural explanation to the E-peak E-iso, or known as the Amati correlation, that is being observed and being discussed quite widely in the last decade or so. So I thank you very much, and I hope there were not too many interruptions.
Yeah, I think we can clap. Okay, so questions from the online participants? Ankur, you can unmute yourself.
Yes, sir. Thank you, sir, for the very nice talk. So I have just worried about, because for each and every GRB, there is some photospheric emission, but for all these GRBs, we don't get this black body spectrum or the thermal component. Why it is so? Means for if the photosphere is present for all these GRBs, then we should get the black body emission or the emission component from the photosphere or this cocoon for all these GRBs, but we don't get it. So what can be the reason for it?
Okay. So the question was, if I understand, is why don't we see the photospheric emission in all of them? So
yes,
right? Is this where is it if it's there? So is that the question? Yeah.
Yes, sir. So I just want to understand, for those GRBs for which the photospheric emission or the thermal emission has not been found, so what is the reason behind it?
Okay, so there are several explanations to that, and I guess that the answer is a combination of a few things. So the first thing is that mostly the analysis is being done on a time integrated spectrum. Now, if you have a photospheric emission which changes with time, as we know it is now, it's just being smeared, right? So this is one thing. The photospheric emission is being smeared in time. Now, there is nothing much you can do because most GRBs are not bright. By definition, most GRBs are very close to the limit of the detector. If you build a bigger detector, you'd still see more GRBs, but most of them would be close to the limit. So there's nothing much you can do against that, right? You just have to rely on the brightest GRBs. And indeed, when you look at the brightest GRBs, this is where you can do time resolved analysis because you do have enough photons. Then you're seeing that the fraction of GRBs that are consistent with having thermal origin is larger. This is one. The second thing, as I pointed out, there are several mechanisms that act to take a pure Planck and broaden it. I discussed one, which is this geometrical broadening, right, which depends on the parameters of the burst and also on the viewing angle. I just want to refer you back to that slide we had over here. This slide, right? This is a spectrum that we obtained from the photosphere, right? This is a photosphere, right? This is a pure photosphere, but what we're really seeing is an aberrated black body, right? So this is the second answer, that the black body might be simply aberrated. And the third answer is that I'm not ruling out the possibility, I'm not ruling out at all, right? That there is also a contribution from additional emission mechanism, mainly synchrotron, because there is a magnetic field in there. I'm not saying it is not. If there is a magnetic field and you put energetic electrons, then synchrotron is inevitable. The thing that is less clear is how significant the synchrotron is versus the photosphere, right? And that really depends on the values of the parameters that you put in. You can put very strong magnetic fields and then the synchrotron will be dominated, or you can put weak magnetic fields. We're not sure what it is, right? We're not sure what is the exact value of the magnetic field at the dissipation radius. So there is also contribution from synchrotron. I kind of neglected it, but if you're asking, I would say the result that I showed previously from the analysis done by Derelli showed that about one third, all these bursts here that are above this line or close to it, these are clearly photospheric. All these bursts, which are about 2/3, I cannot say for sure what is their origin. So I would say maybe it's something like 1/3 pure photosphere, 1/3 maybe synchrotron, and 1/3 would be a mixed. I don't know. We need to continue to analyze those. But
Okay.
this is the best answer I can give you, which is honest, I think.
Yes. And so my second question is, how can we conclude that what is the jet composition? Means it is baryonic dominated or the magnetic flux dominated?
It's a very difficult answer. It's a very difficult question to answer because you need to find some observational signature which will tell one from the other. There are models which argue that, well, basically the difference would be the dynamics, right? So if you have a baryonic dominated, then they carry momentum and magnetic fields carry, it's a different, right? The ratio between energy and momentum would be different. So you could potentially see that when you look at the afterglow. But then again, you have some uncertainty because you're not sure how what is the density of the ambient particles that you run into. So I would say that until now, I don't think that there is a clear evidence for something that could tell you whether it's magnetic or not. It's all the ideas are based on the motivation is based on the problems that you have with the different models, right? So since you have efficiency problems in converting energy, if it is kinetic, then people say, okay, then maybe it's magnetic, but there is no clear-cut signature that can say that.
Okay, thank you, sir. And sir, I have one doubt about the parameter space plot you have shown in the figure, I think, for synchrotron and for the thermal emission. So I could not understand that fact. So can you please explain those two slides? slightly.
You mean this one?
No, sir. I think later.
Sure.
Uh, no, sir. The parameter space plot, the magnetic field versus the radius plot.
Ah, the Hillas condition.
Yeah. Yes.
Ah, that is something very simple. Let me go down. Okay, this one. It's something very simple. If you want to accelerate particles, if you're assuming that there is something that accelerates particles, they need to be confined while they are being accelerated. Or in other words, you want the Larmor radius to be smaller than the source size.
Okay.
If it's a magnetic confinement. If it's a different type of confinement, this criteria does not hold. But you know, the common wisdom of Fermi type acceleration means that you have to have some confinement of particles going back and forth the acceleration region, presumably a shock wave. So the Larmor radius is just the total energy divided by QB, right? And the ZQ is the charge and B is the magnetic field, right? And this needs to be smaller than the source size. So you can just take B and move it to the right, and you have the source size times the magnetic field needs to be greater than a quantity that only depends on linearly on the energy. Okay, so this is this plot RB. Now you just say, okay, for a given energy and for a given species, right? So protons Z is equal to 1, then energy of 10 to the 21 electron volts, then you draw this blue line, right? For irons, Z is 26, and then if you want 10 to the 20 electron volt, then you draw the red line, right? And then you simply take everything you know about the different astronomical objects. You pretty much know the sizes, and for some of them you have some rough estimates of the magnetic fields, and then you simply just draw the dots on this plot. This is first done by Hillas, so it's called the Hillas plot. But the physics is very simple. Just the Larmor radius smaller than the source size.
Yeah, because here the AGN size is much larger than the GRB size. That's why I was worrying, because here the AGN radius is lesser than the GRB radius here. So I could not understand that fact, that why it is so.
I think here I did not make this. I think this AGN refers to the central part of the AGN, right? The black holes. But the AGN, okay. And jets in AGNs, which are of course much larger, they extend up to 10 to the 20 centimeters, right? So here they put it for 100 parsec, right? And the distance will be somewhere in between. I don't know how well they know, if they know at all the magnetic fields in the jets. That I don't know how they have a way of measuring. Actually that I know. They do it via Faraday rotation, so I know where. So they do have actually quite good handle of the magnetic fields in the jets in AGNs. This is done via Faraday rotation, and these are roughly the numbers that I'm familiar with.
Okay, thank you, sir.
Pankaj, you can unmute yourself.
Okay. Thank you very much. That's a very nice and exhaustive talk. So I have a couple of questions. So the one thing that I noticed is about the low luminosity GRBs. There was no constraint about the bulk Lorentz factor. Why is it so?
The bad Lorentz factor in low luminosity GRBs? Because yes. We don't, there is no, you know, how do you know what is the Lorentz factor? How do you know what is the Lorentz factor of gamma ray bursts?
Oh, that is the opacity argument. That is one of the things.
On opacity argument, yeah, there are some other methods. Like if you reverse shock, then that's another method. And there was the method that I worked on by looking at the thermal emission that can also tell you what is the Lorentz factor there, just by fitting a black body. But you don't have any of that for low luminosity GRBs. There are not that many, and there is no clear data at all. We have never seen reverse shock from a short GRB. The opacity argument, again, if you go down these luminosities, sorry, it's not the luminosities. It's in order to use the opacity argument, you need to have photons at the MEV range, and we don't have that. You have photons in the X-ray band. This is XRT, right? 10 keV. You just don't have enough photons from high energy photons that you can limit the Lorentz factor there.
Yeah, so that brings me to the other question, which, okay, so I work in active galactic, blazars mainly, okay. And as you said that if I understood correctly, you mentioned that this X-ray emissions or the MEV emissions are basically synchrotron, is it?
X-ray emission, this could be synchrotron. I mean, many people say that, but it could be.
Oh, so it is still open issue, is not settled, right?
I think so, yes.
Ah,
I mean,
okay.
in the afterglow, I would say, oh look, in the afterglow phase, it's most likely synchrotron. It fits. Again, I did not get into that because that's a whole different talk. The late time afterglow is the part that people think that they understand. This is where things become self-similar and we understand the motion. And there, even there, some bursts are fitted very nicely with a synchrotron model, and some others are not so nicely.
No,
So it's not so clear. Yes.
So what actually intrigued me in, so if you look at the right plot in this slide, if it is synchrotron, the peak is somewhere around in the X-ray bands to ultraviolet bands. Okay.
This is the UVOT. Yeah. Okay. You're
Yeah,
talking about
the right plot. And
yeah.
in blazars, so we typically don't have this high bulk Lorentz factor, but the sources that peaks in this ultraviolet and X-ray bands, they normally are the mostly the sources that are detected in TeV. So I was wondering, why is there no such detection, or what could be a reason in case of GRBs?
Here, what you're seeing is self-absorption, right? This is total self-absorption. No, sorry, this cannot be self-absorption. I'm sorry, this is too high. This is just what we have. This is thermal. This is synchrotron from thermal distribution. This is synchrotron from thermal distribution of particles, right? This is synchrotron. Here you have a situation. What I think you see here is that you have a small fraction of particles that are being accelerated. Many of them kept thermal, and since there is a magnetic field, you're seeing the synchrotron from this thermal distribution.
Okay, so this is basically a thermal electron distribution.
Sorry?
So this is basically a thermal electron distribution that is giving rise to this emission.
Yeah.
Okay. I was confusing probably with the non-thermal, and that's why the question was.
No, I think this what look like a black body. This is really synchrotron from thermal distribution. This would be
yes,
synchrotron.
because there is exponential cutoff. I can see.
Okay.
So okay, regarding this CR, okay, cosmic ray acceleration. GRB as a sources of cosmic ray acceleration. You pointed out that there are protons. So what is the typical energy that they could go? Is it exactly the way you saw it on the Hillas diagram?
You mean how high the energy is that we found of?
Yeah, if these are the sources, GRBs are the sources.
Yeah, we found something around 10 to the 17, give or take. It's difficult to see.
Sorry, I cannot hear anything. I don't know.
Sorry. I'll just show it to you. Yeah, I think it depends on the parameters that you're looking at. But maybe here it's easiest to see. If you go, it depends on where you are. If you're at the radius, if the dissipation occurs at radius of, let's say, 10 to the 15 to 10 to the 16, you can easily, centimeters, right? You can easily get to cosmic rays of 10 to the 17, maybe up to 10 to the 18 electron volts. But I don't think you could get much beyond that. Unless you're putting some additional, no, this is not, you have maybe 10 to the 18.
For protons.
The parameter space becomes very, very limited. So I would say up to 10 to the 17, there is no problem. Above that, I wouldn't count on gamma ray burst. Unless, again, there is something.
Okay, sorry. So the other thing is, if there are protons and photon interaction, as you talked in one of the slides. So what are the current constraints on the neutrino, and what would be the, if there is a detection, or what would be the expectation on neutrino things?
Good question. It's easy to calculate, but we did not do this calculation, so I cannot answer offhand. I mean, obviously, it's quite straightforward to do that, but we did not do it, so I will not answer.
Okay, but I don't know. That is not calculated, but is it below the current sensitivities of the neutrino detection and things, I mean, those constraints?
I think so, because there was, but that's not based on this work. That's based on the fact that there was some constraints from the ice cube 2 or 3 years ago,
Yes.
that they know that they don't have GRB associated neutrinos. They constrain it to less than 1%. So certainly this is going to be less than that. But since I did not do the calculation and I cannot answer the exact value.
Okay. Sorry, Ilan, can I go ahead or?
Could you just hold on?
Yeah, okay, fine.
Yeah. So, Saurav?
Yeah, so I have a question. So it answer may already be discussed. So we get pictures of spectrum of some GRBs where there are a normal peak at say 50, sub 500 or 600 or 900 keV, and there is another smaller hump or bump at lower energy, maybe 200 keV. So this type of spectrum we have seen in papers that they are modeled by a hybrid model, means synchrotron or black body. So how can you describe this? Means they may be synchrotron black body or two broadened black bodies or so.
Okay, that's a really good point. The two, I would exclude the two black bodies because I don't see any physical reason for that. Again, it's what we try to do is to get interpretation of what we're seeing. Now you're right that there are some GRBs that show what seems like a double bump.
Yeah.
Now let me see. I may have it in one of my backup slides. You can get. This is the part that I did not touch in my talk. Get the double bump. Let's see if I have it. Actually, may have something that could be related to that. No, not here. I'm going too fast. Yeah. No, it will not tell us directly, not this line. What I'm showing here in this slide is typical, the spectra that one might get when one considers interaction of photons with particles at different optical depths. So what you're seeing, it's easier to understand when you look at what happens if you're way above the photosphere, so very low optical depths. Then you're seeing two bumps, right? You're seeing the thermal bump and you're seeing a synchrotron bump, and then you're seeing extra bumps which comes from quantization. When the optical depth becomes very large, you're thermalizing everything, so you don't really care. You're still seeing something which looks thermal, and if you're seeing something in between, you'll see something in between. Now, I actually have a slide, but likely not in this talk, so let's forget about that. I do believe that there is, if you have more than one emission zone, right? For example, you have this thermal, which you always have it, but then you have some dissipation which occurs above the photosphere, and this will produce synchrotron. Then you have this kind of a hybrid model, and that is going to be more complex than you think, because then you have the thermal photons from the photosphere will be upscattered by the particles that are accelerated, let's say, above the photosphere. So it's not just two models, one on top of one. But the simplest picture, the simplest picture would be something like what you're seeing here. You have a thermal bump, and then you'll have a synchrotron bump, which could be shifted depending on the magnetic field and the properties of the particles. And of course, what you'll see would be some composite thing. But again, the true spectrum, I expect it to be much more complicated, because these thermal photons would also serve as seed photons for quantization, and they will also cause the electrons to cool down. So it's not just simple putting them one on top of the other, but that, it's kind of a good start to realize what you're saying. So to conclude my answer, I think that the hybrid spectra is definitely something which one might see, and possibly we have been seeing that in several bursts.
Thank you. So how many percentage of GRBs we can see that type of thing? Means what is the probability? Means
and this is a difficult question to answer, because in order to see this, you must have bright GRBs. If the GRBs, remember that most GRBs by definition are very close to the detector's limit.
okay.
Right? So the detector is here. You're just seeing the peak. Okay. Now go and figure out what is that peak. And that is what happens for the vast majority of bursts.
Okay.
There are only few bursts which are close enough that you have enough data to start looking at spectra at all, right? And if you want to do it properly, it's looking at the spectra is not enough, because what you normally do is you look at the time integrated spectra, because you need to accumulate enough photons to do any spectral analysis. But what we need to do really, in order to see this, is to do a time resolved spectra. We need to look at the photons that arrive in a very short time beam. That's what the work with Husne was doing, right? Just looking at the shortest time beams that we have.
Okay, thank you.
Okay.
Okay.
We have a question from here. Shashi is going to ask you a question. Hey,
sorry. Okay. Yeah. Hi, Asaf. Nice talk. I'm SB Pandey. We have met at a couple of occasions, and I think myself and Weikeng Zhang invited you in 2015 to write a nice review article on the similar topic in Advances in Astronomy, if you remember.
Yeah, I do. Thank you very much.
So after that, the field has really evolved, and many new things you just covered. So I have just a quick question, rather two questions I have. One is that if we, like you started that prompt emission spectrum is actually Band's function, and recently we have started realizing that some of them are explained by synchrotron model. Not simply empirical function like band. So if it is a combination of like thermal and then non-thermal synchrotron and then translates up to afterglow, then my question is that how many fraction do you think that now with the increased sensitivity of GBM, if we are able to cover E peak and alpha completely, then are we going to see this for a very large fraction of GRBs where we believe that it's not simply an empirical relation, but it's all synchrotron?
Yes, I guess you're referring to works by Oganessian et al. From the group by Ghisolini.
Yeah.
Yes. Okay. They have modeled the prompt spectra with synchrotron. However, they did it for only a certain burst, which were very, very long. And so they were clearly putting them in like 160 or so burst, 160 or so seconds or so. So this was very way outside of the photosphere, right? 160 seconds, the blast wave would be very far out. What I showed that we did, I did not go into that because this is not my work, and because I just mentioned the fact that there is some revival of synchrotron models. What I have shown is the work by Husne, who showed that about 1/3 of pulses in the short GRBs in the GBM team are consistent with pure thermal. And before that, there was the work by Akuner that showed that roughly 1/4, maybe even more than 1/4 of pulses in long GRBs are consistent with thermal. Okay. So if you merge it all together, as I said, I would say that we have a mixture of both. So possibly something like 1/3 of dominated by thermal, 1/3 dominated by synchrotron, and 1/3 maybe not dominated by each. They will be roughly similar fractions. I guess this is one of the reasons why it's so difficult to get any firm conclusion, because we have this diversity. Again, it's hard to say because these analyses are being done on single bursts, because they are done only on bursts which mostly they are done only on single bursts, namely on bursts that are particularly long and bright, so that we can actually do this analysis properly. Most of the bursts, we simply don't have enough photons to do any analysis, any meaningful analysis.
So, I mean, if true, then do you think that it is going to help in kind of deciphering the possible progenitor, that in long duration GRBs itself there are various classes? For example, in one of your slides, you yourself mentioned that based on the E peak analysis on short duration GRB population itself, you are able to see two different populations. So is it like, are you able to translate it to the possible progenitor, like NSNS or black hole or something like that? That what those two different population, indicate towards?
Yeah, I very much hope so. This is kind of the next logical step. What we're trying to do, essentially, when you think of it, what we're really trying to do is, look at the data. And the data just is produced of photons, right? That's what we have. And then we're trying to estimate the physical conditions, to build up an entire physical picture. And what is the magnetic field? What is the Lorentz factor? How many electrons we have, etc. Now, I think, if you look at it, this is more, to me, in the side of sociology, right? You may know that in the early days of gamma ray bursts, there were hundreds of different models of progenitors. And when people realized that there are two types, right, the short and the long, then natural selection, I would say, most of the models have disappeared, and we're left with two main models which are left, right? The collapsar model and the Newton star merger model, right?
No, but in your population, do you see that further something could be said for possible progenitors in short population itself? Like you have new populations, so almost to translate it to, or it's too early to say like this.
I think it's a very, you may ask the wrong person, because I know that after 1708-17, which I haven't touched here, right? The GRB associated with gravitational wave, a lot of people came and say, look, we thought we solved the problem, and we know that short GRBs are now associated with neutron star mergers. And I did not jump to this conclusion so quickly. I think that it was such a unique burst. In terms of the short GRBs, it was very unique, right? It was not a standard short GRB, that I would say, okay, we do have a clear evidence that this event was a merger, but I'm not sure that I would go and say that this is true for all short GRBs.
Okay.
So how do these works promote us towards understanding what is the true nature of the progenitor? They do give us some clues, I think, but I think we're not there yet. I very much hope to be there in a few years' time, but I would say we're not there yet.
Yeah, sure. One last quick connected question, because there is lack of time. In recently in 3 nearby long duration GRBs, we saw TV emission, the Hess detection and the MAGIC. Recently 1901 Podinsey, the Nature paper, you have seen that the optical synchrotron translated to inverse Comptonized TV emission. That's how it has been explained. So do you think that with increasing sensitivity for necessarily for all long duration GRBs, we must see it?
I'm not surprised that we see it, because first, if you look at the synchrotron model itself predicts that you can simply get this by synchrotron, and of course you get it by inverse Compton. I think what it really tells us, because this has been seen as, this is during the afterglow phase, so this is definitely due to interaction of the outflow with the environment. The main thing it tells us is about the environment. What type of environment we have. It can tell us something about the progenitor. I did make some feats of that myself with a student here, and you can get various solutions. There are some solutions that were already given in the literature. There is some other solutions that were not put there, but they are valid solutions. I think the main, so first, it's not surprising. I would expect them to occur in many bursts. Second, it really tells us more about the environment than about the nature of the outflow. That is my conclusion.
Yeah. Okay. Thanks, Asaf. I will write you later more detail about few more things. Thank you very much.
I'll be happy. You are very welcome to write me, and I'll be happy to answer and discuss these things. I think it's really interesting.
Sure. One more question. So there's another question here.
Yes, sir. So I have a question related to jet within the cocoon model. So can you go to that slide?
Yeah. The last line?
Yeah, jet, where you are showing jet is within the cocoon and
This one?
back simulation result. Yeah, this one.
This one?
Yeah, yeah.
Okay.
So like the morphology of this structure will depend upon the composition of the jet beam, right?
Yes, of course.
Yeah, so it may happen if I launch two jets with the same energy. One is lepton dominated, other one is the baryon dominated. So the baryon dominated jet can impart much momentum and can break out of the cocoon. So in the simulation, how do you take care of that? So what for this particular cold cock or the hot cock, how do you decide the composition of the jet?
Okay, no, this is just an input to the simulation, right? The simulation is essentially it's based on the Monte Carlo method. This is a Monte Carlo simulation of cork material. So you have a material of cork that expands radially, and the particles in the cork, these are essentially electrons that they scatter, so they're expanding, and they may have some temperature. So temperature, of course, associated with the random motion in addition to the bulk motion that they have. And then the photons come from the back of the cork, and they are being interacting with the particles in the cork until they escape the cork, mostly from the back. But they could either escape from the front if the cork becomes transparent, or they can just get lost if they are scattered too many times simply from computational reasons. If they scatter too many times inside the cork, then we simply assume that they're lost. So it's really a numerical setup that we are putting in. So right now we're just assuming that the cork is propagating at a constant Lorentz factor, radially expanding. So the and it has some inner radius and outer radius, which of course change with time.
So the cork has different composition than the jet beam, or the same you're taking?
No, the setup assumes that, so the physical pictures that we have the cork, which is made of material, but for the numerical calculations, the cork is simply made of particles, so electrons essentially, that scatter with the photons, and the photons are coming from behind. Now we are assuming that at this stage, the funnel has already been cleared up, so there is no material in here, right? So pretty much we are relying on these kind of simulations here, let's say this simulation. So we're assuming that the photons emerge or emitted from the inner part of the close to the core of the collapsing star. The funnel is pretty much empty, so they just go through the funnel until they reach this cork, and then they're scattered with this cork. So really, we are simulating this scattering here inside this small cork here.
Okay, there's another quick question, Kundal.
Hi, Asaf. Nice to see you.
Hi, Kuntal.
Thanks for a very nice overview of the confirmation on GRB. I do have a couple of questions, but I think we are running out of time, so I'll write to you separately. But just one question I wanted to ask is regarding this backscattering model. So would this work for all the GRBs? Like, are there any preset parameters there regarding the energies or the range of energies of the Lorentz factors, which would limit it to be applied only for a certain class of GRBs?
I did not hear very well the question. Can you please repeat it again?
So the question was,
yeah, what I was trying to say is this backscattering model, which you explained towards the end of your presentation.
Yes.
Yeah, I was just wondering whether this will be applicable for all kinds of GRBs.
I don't know. You know, it's a new model that we're developing right now. So I don't know. We're just putting this model, and then we'll start to do some parameter check to see how sensitive it is to the different assumptions that we have.
That's what I asked in my question, that whether you have any preset range of parameters here, especially the energies and the values of the.
Yes. Okay. So we put the values which we think are reasonable. So if you see, you cannot really see it here because it's not because I did not put it, and this is just preliminary results. Obviously, right? This is all preliminary, but you can see here that Mukesh did Lorentz factor for the cork of 20 and the jet opening angle of 0.15 radian, which pretty much match the spectra and light curve that we're seeing. So we basically chose parameters which so the radius that we put in of the cork is few times 10 to the 12 centimeters, which is pretty much consistent with the envelope of a Wolf-Rayet star. And what other parameters? The density, we took roughly the density that we'd expect the cork to have from, again, from the envelope of a Wolf-Rayet star. This is, we put as fiducial values of the parameters which we believe could be relevant for this type of setup, which rely on what we know from, stellar evolution. Whether we can play with them, of course we can play with them. We're just putting out different numbers in the code and let it run. We simply have not done it yet because this is so new. This is a work that's not been published.
Amati plot that you have reproduced using this model. So
yeah,
you populate it with the low luminosity GRBs as well. And do you think it would follow the Amati 2006 relation for the low luminosity GRBs also? Yeah.
Yes. Yeah, we can, absolutely. Absolutely. Here you have 20 and 100 and you see how it differs. Yeah, absolutely we can do that. That's a very good suggestion.
Yeah, because it will be interesting to see whether it follows the same Amati 2006 relation.
Mm-hmm. Yeah, these are the preliminary results we have, which do seem to be quite in line with the Amati relation.
I have a few more questions which I can write to you separately.
I'll be happy.
Thanks for the talk.
Thank you very much.
Thank you, Asaf, for a fantastic talk and a very, very, very good participation from the participants as well. So hope to have you sometime. I had few questions, but I will just keep it. It's already 5 o'clock here. So you had your lunch, right?
I still did not have lunch actually.
Oh God, just have lunch. Fantastic talk. Thank you very much.
Well, thank you very much, and I'll be happy to see you in person when it will become possible.
Sure, very much.
Thanks very much.
It's my pleasure.
All right.
Okay, yeah.
And feel free to write me if you want to have more questions. I will be happy to continue them with you.
Sure. Okay, bye.
Okay. Bye-bye.